All right. Hello. My name is Matt Bankston. I also go by Matti, whatever you prefer. And I'm a senior front-end developer at OP Pohjola, we're one of the largest banks in all of Finland. And there I work on the front-end architecture team, where I primarily work on build systems, tooling, making sure the platform is there and ready to support the hundreds of development teams that we have whenever they do front-end development. So I spend maybe a bit more time in like Node.js land than kind of like browser land, so to speak. But we make some cool stuff. Today I'm going to talk about inter-process communication in JavaScript. This is a talk that I gave a couple of days ago at HelsinkiJS, and it was a great time, great event. Unfortunately, we were not recording or streaming it, so it's sort of lost to the ether. Hence, figured I would do a recording of the talk so that more people can consume it. It's quite a code-heavy talk, so I'm going to try to include some timestamps at the bottom. Try to put them in some good spots because it's also quite... I try to make sure that everybody has the correct context, right? Inter-process communication, just like splitting things across multiple processes in general, it seems like is not necessarily as well known of a trait of Node.js apps as you might think. It's a really, really useful pattern, but it's actually quite difficult to find a lot of people that have hands-on experience doing it somehow. So I want to make sure that everybody has the correct context. So there'll be timestamps if we're going over something that like is super familiar to you and you're like, I really don't want to hear this dude yap about this basic thing. Feel free to skip ahead. All good. All of the materials as well are available on GitHub. Presentation is available on my website at ipc.bangsfort.dev. And it also has a link to the GitHub from there too, so you can access it from there. But yeah, let's get into it, man. So inter-process communication. What is it? Or like, what are we talking about here? Well, every time you run node index.js, that's essentially spinning up a new Node.js process, which is processing the information. It's running your program. Now, say you have two of those. Inter-process communication is sort of like giving a phone to each one so they can text each other, right? It's just being able to communicate. It's the act of communicating between these different Node.js processes that are running. Now, you might wonder, like, why would you need to do that? Well, a big part of why you would want to do that is performance. We're in a single-threaded environment, right? We have to be kind of careful about the amount of work that we have our main process doing. Now, if we load up that main queue of ours that's trying to empty with just a bunch of stuff to do, it's trying to get those things done, and it has less resources to actually respond to user input, react to different events happening, trigger re-renders, trigger this, trigger that. So we don't want to do that. We don't want to provide the user with a janky, bad experience, a laggy experience. So we can move some of that stuff into a separate process, free up that main process so that it can actually focus on the user experience. Another really kind of like nice usage for it, which is maybe more prevalent in like for example, Electron world, is sort of almost like sandboxing specific integrations, specific functionality. In my spare time, I do a lot of sim racing and just like hobbyist programs that are mostly consuming game data from their SDKs. And you usually have to have some sort of like Node add-on module, C++ add-on module for actually consuming that content, consuming that information, which you then have to surface in some way. And that can be a really volatile process. It can be a real pain. But a really good thing that you can do is toss those into a process, their own isolated process. If something goes wrong, if they crash, if they panic, if something happens, you can gracefully recover from it, try to reinitialize everything. You can sort of like really own that life cycle of sort of your SDK process, so to speak. And provide a little bit of guardrails around it, right? So those are two really good use cases. And again, this stuff is all, we might be in single threaded land, but like this stuff is available. We have child processes in Node. We also have the worker threads and VM module. Like all of these are also kind of like a form of this, and all of the patterns we're going to talk about apply to those as well. We're just going to focus on child processes. And not to mention, like, we have it in the browser as well. We have the worker API. We have web workers, shared workers. You can do a lot of things. You can offload a lot of kind of like heavy processing in all these different environments. It's really cool. So let's look at like an example of what this actually kind of like looks like in code. Now, this is modern engineering. So, you know, adding some numbers together is a pretty tall order. You know, we're gonna end up bricking my CPU here, I'm pretty sure. But let's say we want to have an example where we have some numbers and we want to add them together. But we're afraid of blocking up our main thread. So let's spin up another process to do the actual, you know, complex calculations that we need. So the main process will grab the numbers that we need, or it'll provide the numbers that we need, send those to this child process, which will do the processing and send the result back to the main process. Now, what does this look like data-wise? Let's first think of like the data needs. We need two messages. We need a message going from the main process to the sub process. Then we need another one going from the sub process to the main process. Send the input, get the output. Now, that can look something like this if we just sort of scaffold something out real quick. We can have a add numbers message. This is the one going from the main process to the sub process. You can have a result message for the process, sub process to the main process. Sounds good so far. We include a type so that we can sort of identify what these are, but they're really straightforward. Pass some numbers, get a result. Now, in Node.js, it's actually not that complex of code to write either. We use the fork method from child process, pass it a script, and we get a nice juicy reference to the child process that is sort of like spawned. Now, this is going to have IPC built into it. Basically, it's going to have all that stuff ready to go. And luckily for us, it's an event emitter. So we can just add a listener for the message event. That's going to be sort of our bread and butter for this entire thing. Now, in this case, we know it's just going to have one message that it's expecting, and that's the result message. So we can go ahead and toss that in as the type. Then we can just log the result. Easy. To initialize this entire thing, we have that nice juicy reference to the child process, so we can just call send. Pass it some information, pass it the numbers that we want it to do, to send over to the other process. Now, we do have to sort of like, the typings are a bit funky, where you do sort of have to assert what type it is, because it doesn't care. Like, it's just trying to send a text, right? It's just going to JSON serialize by default. You can have more advanced serialization, but we're not going to get into it. It's just trying to send some data. It doesn't care what you give it. So that's a bit frustrating, but it is what it is. Now in the web, looks the exact same. It's just slightly different. We have worker instead of fork. It's a class instead of a function, but we can still just pass it a script. We get a nice juicy reference to an event emitter again. We can add event listener instead of on. Add event listener, listening for the same message event. And then we have like, you know, some browserisms here with the payload of the actual event, a little bit extra stuff. We have one extra property to go through, but not bad. Instead of calling send, we're calling post message, passing the data through. Now this is going to use the structured clone algorithm for serialization, but we're not really going to get into the ins and outs of the serialization and stuff. Like, most of your JavaScript objects will work fine as long as you're not using like instances of nodes and functions and stuff like that. Should be fine. But yeah, that's all we need. So both of these, like, you can kind of see like they match up almost perfectly. It's just sort of the naming of things. What does it look like on the other side of things? Our actual like child process that's doing the work. Well, actually, really straightforward again. We have, for the node side, process, the global sort of like process object that you're usually getting like CWD from and stuff like that. Well, that's an event emitter. And again, when we spawn this script from fork, it's going to bake in all of the IPC stuff for us. So we can add a handler for message. And if something tries to send a message to this process, we can react to it. Right? So we do that right here. We know it's going to be the add numbers message. So we can go ahead and do our really complex calculations, brick my computer, and then send the result back. And again, this one using the global sort of like process instance. And because this is a child process that has that IPC baked in, we have access to the send function. It's not always there. Like if we try to do that in our main process, send isn't going to really exist, but we're in a child process, so it does. And in the web worker, surprise, surprise, it's identical pretty much, apart from names of functions. Now here we do add event listener. There's a global add event listener. Expect message. Again, the add numbers message, we do the calculations. We post message the result back. Instead of process send, we post message. Like, it's pretty straightforward, right? Like it's not too bad. And this sort of shows us that even across the different runtimes, IPC just is essentially the same fundamental things. Like we're just sort of working with these event emitters in like a predefined event. It's really, really nice in that respect. We don't have to worry about the ins and outs. We just sort of, we initialize it. We kind of like tell it, hey, please create this thing. And then we can talk to it. It's really nice. Now, side note, we are going to be doing Node.js focus from now on because it's less verbose. It's easier to fit the code on the slides. But so far, so good, right? Let's make a slight adjustment, though. We have 2 messages. Let's bump those numbers up. Let's get a third one. Right now, let's say our worker process is going to be emitting an event every 60 seconds with some metrics for our analytics. We really care to know about how much intense processing this worker is doing. So we're going to emit that event. But the thing is, like, implementation wise, it's not really that complex. We just have a set interval in our worker, grabs the data, sends it. Not too bad. But there is a problem in our main process. This function is no longer accurate. This is not a reliable function signature anymore. So we don't have just one message. We have 2 messages now. Might be thinking that's fine. Just add the type, right? We have the type in the object itself, so we can add an if statement to make sure that we are responding to the right event. What's the big deal? Like, this doesn't seem too bad. And you're right. Like, it's maybe a bit inconvenient if you have a lot of different handlers. Like if you don't have just one message handler in your code base, you kind of have to do that in all those different places. Like that's kind of inconvenient. But it's not too bad, right? Like we've got 3 messages, all is good. What if we add 2 more? Now we want to support subtracting, and we have a subtract numbers. We have the subtract numbers result. We want to have the result, but you might also think like, well, that sounds a bit silly to have an add result and a subtract result. Let's just have a result, and it could even like have the operation in there. Like, sure, yeah, we could do that. But side note, now we have to go back to all of our dispatches, our event dispatches, and our event handlers, and make sure that we change the type. But again, it's fine. We don't have too much going on. It's not too bad. Then we get another one. Now we have multiply numbers. We're really exploring new domains here. Then we have another one. And then we have another couple. Now, this is an actual kind of like screenshot of all of the events from like I was mentioning, I do a lot of like hobby, kind of like Electron apps consuming game data. This happens to be from a simulation racing app. And it can get out of hand really fast. As the code base grows, it can get really, really, really hectic really quickly. Like I mentioned, like this is a real list of all the IPC like events and calls from an actual production app that I was working on. It's got 24 unique events. So it's sort of just like, hey, this thing happened in case anybody wants to know. And then it has 17 unique IPC calls. So that's like the main process kind of like asking for something. Here's some information. Please give me the result. That's 41 unique messages, right? That's a couple of messages. And if we were to do this with the same sort of patterns that we were doing in our example, then each one of those IPC calls would have to have a result message as well. Not great. Like this, it's getting a bit out of hand. And speaking of IPC calls, like, what if we want to use the result of the IPC calls sort of procedurally? Like we want to be able to just call something from the other process and then have the result to actually use it. Like, how do we do that here? We just have a generic message. Like ideally, we would be able to just call a function, await it. When the promise resolves, we have our result. That's the dream. We can then just sort of use it like an API. Well, now we're starting to see some of the issues that kind of arise. As more and more events are added, the more complex the handlers become. The more complex the dispatching becomes. And not to mention, like, this wasn't kind of like, we didn't explicitly go through this, but the typing of send and post message doesn't really enforce anything. It's sort of on you to assert that it's going to be of some specific type. If you've got 41 messages, what happens if you forget to assert or use the wrong interface? In one of those 41 kind of like event dispatches or call dispatches. Well, that's going to be a fun debugging experience, because we also have to remember that, like, when you add a typo to like an event type or something, when you're doing IPC, that's not a runtime crash. It's not a build time crash. That's a silent runtime error. You're just going to be sending a message that's just never going to be responded to because you don't have a handler that knows how to handle or like knows what it's looking for. It doesn't know to look for that typo. That's a bit of a problem. And again, as we just went through, like the tracking the result of a message that we have sent from one process to another, tracking the output from an input is difficult. So how do we do this like in a sane way? How do we actually get to a point where we can use IPC without ending up like me with no hair? Like that's the goal. I don't want people to lose more hair. So let's start by fixing the events. So what do I mean by that? Well, we want to first make sure that all of our events adhere to the exact same schema. We want to be able to reliably detect and handle them. And then we also, let's just get some dummy types set up so that we can start visualizing this, right? It's just easier when we have some actual visualization, like sort of data to visualize how we want this thing to look. Well, we can have an interface for IPC events. That should have like an event name and a payload. Sounds good. The listener is just going to accept an event, an IPC event. That way you can do something with it. Fantastic. Looking good. Now, what we'd also like to do is add a little bit of security and provide like a sort of single source of truth, so to speak. So maybe we want to wrap our worker with some sort of API and sort of almost use it to as like a factory to create a nice, succinct API that we can then use. We have like a single access point, single source of truth, kind of control the lifetimes of the listeners, allow listeners to opt in to only specific events, not having to worry about any boilerplate. It can just be like, hey, I want this function to get called every time this event comes in. And what's really nice as well is we can draft a sort of more generic interface for this. That way we can implement the same thing for both web workers as well as Node, using the same sort of like fundamental interface. We'll do the typing a little bit later. Let's first focus on like making the events. So we come up with this. We have this worker event emitter, which has add listener, remove listener. They both accept an event name and a listener. Then we have dispatch for sending an event. It accepts an event name and a payload. And then we have cleanup. Now I know what you might be thinking, which is like, are we really doing this? Are we really making an event emitter for an event emitter? Answer is yes. Let's move on. So what does this actually look like? Well, You can also skip ahead, by the way. I will make sure that the timestamp for the typing stuff is there. So if you don't want to, if you know how an event emitter is implemented, go ahead and skip ahead. But so let's make basically a factory function, pass in a worker, get an event emitter back, a wrapped worker back. We'll need a listener map here, and then we just return an object with those things. You could also do this via a class and just implement the interface on that class. Totally fantastic idea. I feel like there's stronger opinions on classes than just a function that returns an object, so we're going to go with that. But both work just fine. Go with your personal preference. Also, quick note, here we're using set instead of an array. You can use either one. We're using set here because it's a bit simpler to sort of demonstrate. It's a bit simpler to use as well. It handles deduplication for us, for example. Just adding and deleting is easier, but it might be like marginally slower than a raw array. Go with whatever you feel like. So let's start with add listener. Well, quite straightforward. We're sort of doing a lazy event adding approach or event listener approach. So we're going to first check, is there a set of listeners for this specific event? If there's not, we're going to create one. And then after that, we know one exists, so we can go ahead and add the listener to the list of callbacks. Easy. Remove listener, pretty much the exact same. It's just if there is not a set, we don't have to do anything. So go ahead and exit out. Otherwise, we're going to go ahead and delete the listener from the callback, from the callback list. You could also here, if you wanted to, you could delete, sort of like clean up the set. But in most cases, it's not really super necessary. But if you're really, really in a situation where you want to make sure everything is as tight as it can possibly be, go for it. Always depends on what your situation is. All right, dispatch. Now, dispatch is going to be really easy because we just need to toss those two things into an object. We can provide some kind of like strict typing of what that structure looks like, and then we have to send it over the worker, right? There is one caveat here, which is we do have to sort of like act like this might not be there, and that's specifically because of the Node.js.process here. We added that in, both child process and Node.js process, so we can use this same exact API across all of our different sort of like processes. We can have it in the main process. We can have it in the child process. The exact same API, exact same sort of like fundamental kind of framework, so to speak. So like I mentioned earlier, on the kind of like Node.js process instance, send is only on there if it's a child process. So that's one thing to note. That's why that's there. Let's do a quick little recap of what we've just done, right? So we wrapped our worker and exposed essentially an event emitter. Create a map for storing the listeners of specific events. Add listener and remove listener. We just add the list, add the callback to the list of callbacks for that event. We remove it on remove listener. And then dispatch, we take the name and the payload, send them through the worker. Easy. Now, this implementation is intentionally basic. There's more things that you can do. There's optimizations that you can make, but we're just going to keep it simple for now. And additionally, like if you want more features, if you don't want to maintain your own event emitter, you're just like not interested, use a library, but make sure that you use a library with good kind of like typing support. Highly recommend event emitter 3, and even the base event emitter from Node.js, for example, really good. And you should be able to do the same patterns that we're going to be doing with just using that as like your sort of like the backbone of your sort of like API. But highly recommend both of these. If you want to use something that is compatible with both Node and web, event emitter 3, fantastic choice. So now let's finish up the event emitter. Let's hook it up, right? So we have this lovely worker reference that we're getting. Let's use it. Right? Let's add that listener to it for the message so we can actually start kind of like filtering out these messages to their correct callback, their correct listeners. First off, one thing that we want to do is we want to make sure that we have a callback that we can actually reference directly. That way we can remove it later. If we were to just inline it here, we can't clean it up. We can't remove that when we want to sort of like perform cleanup. And in fact, let's go ahead and perform cleanup now. So we want to remove the message handler that we've added on. We also want to remove all the saved listeners, clear out all of those sets so that everything can be cleaned up. We're not holding on to any additional memory. Just let it all get cleaned up. We all survived 2020. We know how to clean up our hands, wash our hands. You know, that's all we're doing. So now we go back to the worker message. What is this going to look like? Well, first off, we want to make sure that we are kind of operating on messages that we can actually use, messages that follow the schema that we've provided, that we've defined. So in this case, we're going to check, does it have an event name? If it doesn't, we go ahead and return. This allows us to sort of build on more and more things onto the same exact sort of like IPC channel without them like kind of like fighting each other, right? Next up, we want to make sure, okay, let's grab the event name from the message because we believe this is one of our IPC events. And then we're going to go ahead and use that, see if we have listeners for that particular event, iterate through all of them, call them all, pass on the message. Great. So where are we? Well, we started off with this on the left. We started off with the, why is this showing? There we go. We started off with this task process. We add the listener directly onto the process. We then have to sort of like filter out the messages and filter out how we handle them in that sort of like listener. Then we have the send where we had to sort of like kind of enforce what we're trying to send. Now we are over here on the right side. So we initialize the task process. We toss that to our sort of like factory function. We get this nice event emitter out that we can then just add listeners to specific events without having to do any of the boilerplate. And we can pass this reference around our code base, and we don't have to worry about conflicts. We don't have to worry about not cleaning things up. We just pass this around. Things can then start adding listeners wherever they want to. All is well. You can even dispatch. So now let's fix the types. I feel like we've done a good job with our baseline implementation. Let's fix the types. And fair warning, we're going to start doing TypeScript things. So if you do not like generics, you might want to just bail out now. You have my permission. I apologize. So typing an event system, what does that kind of like look like? What do we need to do there? Well, we need to kind of have a single source of truth about what our events are. We're going to use a type map for that, which is essentially just a big interface. And then we're going to use generics. That's pretty much it. Our main goal is just to tie the name of an event with its payload, right? We can do that with an interface. We can just have a big interface where the key is the event name, and then whatever type that has on the right-hand side is the payload. Easy. Then we can just use generics and helper types to sort of create new things from that. So what does this kind of look like in practice? Well, let's start out with like a little basic example. We have this type map here. We have two events on it, event A, event B. Event A is an object, which is going to have foo, which is a string. We have event B, which is going to have bar, which is a Boolean. Easy. Start with our first sort of helper alias type, event name. Ooh. Now we're cooking. We are going to be accepting the type map, key of map to get all of the, it's just going to be extracting the key names, right? Those are essentially our event names. And as you can, I'm pretty sure if you have been doing some TypeScript, you know about key of, so we're not breaking ground yet, but just to kind of like show, we now have some way of sort of identifying what those event names are. We have an invalid one here, and TypeScript is now telling us, hey, you messed up, bucko. Fantastic. Let's move on. Now let's grab the payload. Here, doing the same thing. We're having two generics this time for this kind of like helper type. The first one is going to be the type map again. The second one is going to be name. We're going to name it name, but it's going to extend that first one that we have. So it's going to extend essentially the list of all of the keys of the type map that we've passed in. We're also going to, and this part's quite important, we're going to default it to the list of event names from that type. Now, what that's going to allow us to do is if we use this type to access our map, it should provide us with a lot of really nice inference. TypeScript is going to basically do all of the hard work for us, which is great. So now if we go a little bit deeper here, we want to try to enforce that our type is sort of in line with what we want it to be. We want to enforce a specific structure. So we have here an extends, which is basically just like an if statement for TypeScript. We're going to make sure, hey, this needs to be some sort of like record. It's going to have a string and some type of value. If this does extend it, we can go ahead and return the map. It adheres to our sort of like structure. Otherwise, it should never get to this point. This is sort of just like a fail type. And now we can see we have type safety for our actual payloads. And now this is what I meant by the equal sign is quite important. We don't have to actually include that this correct payload is event A. TypeScript can tell. TypeScript knows, oh, this has foo. Foo is a string, so that must be event A. This matches with this type map plus the event A type signature. Fantastic. And on this one, for example, now we're sort of saying this needs to be the payload from event B. But instead of a Boolean, I've put bar as 42. And TypeScript's like, dude, what are you doing? Right? Really cool. So now that's everything we need. Those are the building blocks that we need to generate better types for our type system, for our event emitter. So now let's go back to our messages, right? We had these were the two messages coming from the sub process back to the main process. We had the result one and we had the worker metrics. Let's move those into a type map. So same exact kind of like signatures. We have result. It's going to have operation and the result. Worker metrics, that's going to have the uptime and the calculations. Fantastic. Now what we can do is we can take those sort of example, like kind of helper types. Let's just apply them to this exact same type map. Then we're going to have, again, our event name here. Same exact thing as pulling out all of the event names, essentially just extracting those keys from the interface that we provide. And then payload, exactly the same as the one we just looked at. It needs to be a record with string and then some value. Now, let's go ahead and make our IPC event interface into make it type aware. Well, actually pretty easy. First things first, generics. Generics for everybody. It's our favorite thing ever. We're going to make sure that the first one is, again, our type map. Then the second one is going to be the event name. And it's going to be the exact same pattern where we extend all of that helper type for the keys of a given map. And we're going to also default it to that. So now, since we are also using this type for event name, whatever string we put in for event name will essentially determine what this type is. And since we're then using that type inside of the event payload here, it's going to try to use that type that we've provided by putting a string here to index the event payload type, which is going to give us some really nice type safety. And you'll see if that just went, we'll see soon. We're going to do the exact same thing with the event listener callback. The exact same thing. Just need to add those two generics and then toss those into the event type. So we also, if you'll remember, we have that record, the sort of like listener callback map. That one, we're going to run into some typing issues if we don't do anything. So we want to make sure we have a type for that as well. And this one's going to be quite simple comparatively. We take in a type map and then we just iterate through all of the keys and we basically generate a new type where we say for each key in this map, we're going to have a key with that same key and it's going to be optional and it's going to be a set of event listener callbacks, which are going to have that same key. So that way we can index what the actual type is going to be. Great. Now, I'm sorry. Let's take a deep breath. I know it's really kind of difficult to sort of get all of that thrown at you. So let's take a deep breath, and then let's go straight back in. Now let's make our base interface type safe. Well, first things first, generics. We have this worker events. That's going to extend our kind of like base type map type. And then from there, let's do add listener first. So what do we need to do? Well, we have the type map. We have event name here. So we're going to do the same trick. We're going to have a generic for the event name. We're going to apply that to the type of event name. That way we get that same sort of like inference going on. And then the listener is going to be the listener with that same type. We're going to pass that same generic over into there. Easy. Same exact thing for remove listener. And then dispatch is slightly different though. Now, I will not lie. When I was initially making this, I completely forgot about dispatch. Completely forgot. And that's kind of a problem because we don't have everything we need for dispatch yet. We have to remember that dispatch is sending a message to the other process. All of these types that we've provided just now are what we're expecting to get from the other process. So we need another generic. And that one is going to be this. We're going to call it this event. The namings are a bit funky, but bear with me. Now, worker events will be the events that we're expecting to receive. The this events are the events that we're expecting to emit. That way we can then use the same interface on both sides to describe the incoming and outgoing APIs. And then we can do the exact same thing that we've been doing everywhere else. We just expect the event. We do the sort of like passive event typing for the event name, and then we pass that to the event payload. Now, we've done the interface. Now let's update our implementation. We're almost there. So first off, we need to add those generics. We also need to make sure that our return type with the interface also carries those events or the generics into it. That way we should have the types persist all the way through. Then we can update our listener map to have our nice juicy event listener type that we created. Fantastic. And now let's look at the actual handling of the worker message. So this is what it looked like before. To make this kind of like fully type safe, it's quite simple. We just pass through the types that we're expecting into the IPC event. We do have to sort of help TypeScript here because the second we check, is this not equal to type of string, TypeScript is going to sort of like assert that event name can be a string. So it's going to be the whole key of the map, but it's also going to be a string. So we do have to sort of give TypeScript some help and say like, hey, trust us, bro. This is string, or this is the event name. But that's all we have to do here. So not a whole lot. Now, if we look at all of these down here, we can fix these up really quick, really easily by removing the types. Because we have all of those defined on the actual core interface, so we don't need to explicitly say what they are. And that will give us a lot better inference, and it'll make it a lot easier to use as well. Now, there is one thing. We don't have to do anything, by the way, to add listener and remove listener. Once we remove the explicit types, we're golden. We don't have to do anything. But there is some stuff we have to do dispatch. But luckily, it's not a lot. We just tell it what kind of event it's going to be. That's pretty much it. So we just have added this generic here for this event. Again, the outgoing messages. Last up, the cleanup function. Again, very straightforward. We just have to help TypeScript out a little bit. That's it. So in this case, whenever you do object.keys, the result is always going to be a string. It's going to be an array of strings. So we again have to sort of help TypeScript and be like, hey, we promise this is an event name. But now we've done all that. What do we get? What does all this get us? Well, it gets us some really nice type safety. So now that nice little API, like before it was just sort of like a syntactic sugar, right? But didn't really give us anything. And now you can see we actually can get full type safety and a much better developer experience where our IDE, our VS Code and everything can actually tell us what's available. So if we look at the payload here, it's going to be the payload of worker metrics. So it's going to be type aware. And the types for all of the available messages are still there as well, which is really nice. And if we accidentally make a mistake, we forget to update some payload, we put something else in, TypeScript can now tell us at build time, hey, you have a bug, which is super valuable when it comes to these big, complex IPC code bases. We also get this for the dispatch. So not only on the other side of things, but also when we're dispatching the messages, we get the exact events that are available and we get the payloads. So there's no more concern of accidental typos causing chaos at runtime, which is really nice. It's a game changer. And you can actually see as well here on this one, this is again that sort of like outgoing events type here. We have it there on the second generic. And if we go back, it was on the first one here. So that's really cool. Now typing done. We're almost there, I promise. So tracking the result of a message. This is the last thing that we haven't gotten to. And luckily, we can just reuse a lot of what we've learned within this last 40 minutes. I apologize. But it's gonna be good, I promise. So tracking IPC calls. What do we need? Well, we want to be able to call these things as if they are an API. We want to just get a promise, and that promise should resolve with the result when it finishes. So how do we do this? Well, we need some sort of ID for each response, for example. The other process should then know to attach that ID to the resulting message so that we can track this thing from input to output. And we can use the same typing tricks that we did before to actually get full type safety here. We want something like this. We want to be able to have some sort of API where we can call some sort of function, IPC function. We provide it with a thing, with a function name, the arguments, and then we just await the result and we can use it. That's the goal. So let's take a look at what we've got. This is what we previously had. We had all of these add numbers, subtract numbers, multiply numbers. Then we had the result message, right, for coming back. Well, now we can just create a type map again. This one's going to be our IPC APIs. It's going to have the same stuff, except this time, because we're kind of now designing a type map for sort of an API, we're going to have function signatures. So numbers, that's going to be an array of numbers. They're going to return a number for all of these three. And just for the sake of testing to make sure this all works, let's go ahead and add say hello as well. So we want to be able to provide a name and then it will return with hello name. I know we're really breaking new ground on what's technically possible here. So now let's look at what the actual messages might look like. Well, we need one for the request, one for the response. Makes sense. Well, these can look like this. We have IPC request message as our first interface. We can have a call type, which is how we can identify whether something is a response or a request. Then we have the ID. We're going to have it just be a number that increments every call. You could do something more complex. You could do just UUIDs. You could do some sort of generated ID, whatever you want to do. We're going to stick with something simple and just do an incremental, kind of like infinitely incrementing ID number. Then we're going to have the function name of what type of, what's the function going to be, and then the arguments that we want to pass to it. The response, pretty much the exact same, except it's going to be a response call type. It's going to carry along that request ID. Then it's going to have the result if it is there, otherwise an error. Okay, that way we can actually surface these issues if there is an error back to the user, back to the developer. And now let's think about what helper types we're going to need. Well, we're going to need a type map first and foremost. We're going to want the extractor for getting the name of the API functions. That's going to be the exact same as the event name. So we can already implement that. That one's cake. Then we want the full kind of like function signature, right? What this function is going to look like. That way we can actually add that type to where we need it. Then we also want an extractor for the arguments for the type as well as the return type. So let's look at those last three here. So we have the function signature. We're going to use these exact same patterns that we used before. We're going to have two generics, one being the map, the other one being the sort of like passive optional name extractor type. And then we're going to use that to index this big type map. And in this case, we want to kind of enforce that it is a function. So we're going to have it extends args any, return any. If it adheres to that signature, go ahead and return the type. Easy. Nice. For the args, now we're just going to just piggyback straight off of TypeScript. For the args, we're just going to use the parameters helper with the API function signature that we just implemented. And we're just going to pass those two generics. Easy. Same with return type. Instead of using parameters, we're going to use return type this time. Easy peasy. So now let's look at our actual request and response types. What do we need to change here? I'm sure you can guess, but we're going to be giving everybody some lovely generics. So again, the type map, the API kind of like name extracting, and that's going to be, again, optional, so we can get that inference going. The API name, we're going to have that be the function name. So whatever function name we pass in here is going to be used to index the type map, and we can then pass both the name and the map to the args type to get typing for the arguments. For the response, it's going to be very simple or very similar. Use the exact same tricks, map, API name. This one's going to be inside the result is going to be API function return type. And that's it. That's all we need to do. So now that we have all those helpers out of the way, let's focus on the API. Let's do something very similar to the previous one where we have an interface. Now this interface is going to be a little bit more simple than the last one. We're going to have a way to call an IPC function, like a remote function from the other process. We're also going to have one for registering something to handle a specific function. Then we're going to have a cleanup function. Side note, you would probably also want an unregister IPC handler here as well, just to be on the safe side. But it's going to be like exactly the exact same implementation as for the event emitter that we did before, pretty much. So unfortunately, I didn't really have a lot of time to actually implement or like write this entire thing, so I left that one out. But it would be a really good idea to also have that. Anyway, keeping on, we're going to again have those two generics that sort of identify what our expected API is going to look like, as well as the API that we're providing. And both of these are going to extend the API maps up here. And then we're going to do the same stuff that we were doing on the other, on our other kind of like wrapper function. So most of it is just, we kind of use that naming, grabbing the kind of like name, putting that in as the function name parameter, and then using that to pass it to everything else. Here we're going to spread so that we can actually get a really nice sort of natural feeling API where all of the functions that, or all of the parameters that come after the function name are sort of treated as arguments. So it's going to be a really nice little API. And then we're going to have that be a promise that's going to resolve to the return type of the API with the function name. Let's breathe a second. Now for the actually registering what is going to get called on the other process, pretty much the exact same thing. We're going to extract the name of the function from the function name argument, and then we're going to pass that to the function signature helper. Easy peasy. So let's go ahead and implement this now. We've got all of the pieces. Now it's just implementing it. So we do the same thing. We have this kind of like factory function, so to speak. that's going to be create worker IPC API. We're going to pass it 2 type maps. Same, we're going to pass it the sort of like the process or the child process. And we're going to turn this worker IPC API with these 2 type maps. We're going to have a listener for the worker messages. We're going to return the call IPC function, the register IPC handler, all that stuff. Now, let's do the registering of IPC handlers first, because I think it might be a little bit easier. So we're actually going to do calling. I think this is the wrong highlight. I apologize. I must have broken that. So we're going to do calling IPC first. What are we going to need? So we were talking earlier about how we're going to need some sort of ID, and we're going to keep it simple. We're going to use a number that's just going to increment every single time there's a call. So when we create the function, we want to also create a number that we can then iterate on. We can just increment it nonstop. And then in our call IPC function, we're going to create the request message, or like sort of request object. And that's going to have the call type, it's going to have the function name, the arguments. We're just going to increment the ID, and then we can send that across to the other side. Easy. But how do we get the response back? Like, remember, when you call this, you should be getting a promise back that's going to resolve to the object, to the result. Well, we can use a promise with resolvers. So we can use like an externally resolvable promise. This API, promise with resolvers, is available as of Node 22, I believe it was. And there's a million shims. There's a shim in the example inside of the talk repo. You can go ahead and feel free to grab. But it's really great. You call it, you get an object back with a promise and with its resolver and its rejector, so that you can externally resolve or reject that promise. Really useful API. So happy that they actually made that part of the sort of like Node.js APIs in general. Really, really great. But yeah, so we're going to go ahead and create an externally resolvable promise that should resolve to the return type of the particular function. And then we're going to return it. We're going to turn the promise from that. We also need to save the resolver though. So up in our main function, we're still going to have some sort of map. And this one's going to be quite easy because we don't have to have all of the sort of like necessarily the type awareness. So in this case, we're just going to have a map where the key is the ID, and then the sort of value is always going to be the resolvable promise, the resolvers, the rejectors, all of it. So then we can just go ahead and save that. Let's just toss it there, cache it. So this is sort of what we end up looking like. We have that call logic. We now have these waiting requests and the ID counter looking good. So now what do we need to do next to kind of complete this cycle from the calling perspective? Well, we need to handle the message that comes back, the response message. So let's go ahead and do that. So inside of the worker handler, the message handler, we're going to be expecting either a response message or a request message. The response message is going to have the worker API type map. The request message is going to have the this API type map. We're going to ignore the irrelevant messages. So if they don't have a request ID or a call type, we don't care. This way, we don't actually have to worry about this API, this wrapper, interacting or fighting with the event wrapper. They can both handle their respective kind of like APIs without affecting the other. So we then know we have one of the types, either a response or a request message. So let's handle the response one. So if call type is response, we're going to go ahead and handle that. Now I had to do some hiding because it was hard to fit everything on the screen, but bear with me here. So when we have a response message, what do we need to actually do? Well, we need to retrieve the promise first and foremost. So we have the request ID. Let's go ahead and try to get the kind of like resolver, the promise, from our kind of promise map, our waiting request map, using the request ID. If there isn't one, it's probably already resolved. There's been some issue somewhere. So let's go ahead and just early return. Otherwise, we can go ahead and delete it from the map now so that we don't resolve twice or reject twice. And then we check, does it have a result? If it does, we can go ahead and resolve the promise. We have access to the promise and its resolvers, so we can go ahead and resolve it or reject it, depending on what the situation is. And that's it. We now have that full cycle. Good to go. Now, let's look at what registering looks like, the other side of it, what the other side of the process, the other process is going to do. Well, we're going to need to handle a function. So we're going to have to take our event listener map and make some changes to it. We're going to make an API handler map, which is going to do the exact same thing, kind of, except instead of having like a set or an array of handlers, we're going to have just one. So do the exact same thing. We're going to create a new type, a sort of like lazy initializing type, which is going to have every single one of the keys from the API as well as a registered handler which adheres to the function signature. We're going to go ahead and add that. So now we have an API handlers map as well. And inside of register IPC handler, we just save it. That's it. We just save that specific handler with inside of our handler map with that particular function name. Easy peasy. But now we have some more things to do. So first, we are almost there. This is the final stretch. Let's take a deep breath. Okay, let's get back in. So now we just need to hook up that final part, the sort of like request handling, right? So we're gonna go back into our handle worker message, and it looked like this before. Remember, we check to make sure it's a relevant message, and then we handle the response. Now let's handle the request. So first things first, we want to start kind of drafting our response. We want to get the basics of our response ready. So we're going to go ahead and create a partial of the response with the call type, the request ID, the kind of like, the fundamental things that are never going to change. And then we're going to wrap the rest of this with a try catch, because we want to make sure that we don't leak any sort of unwanted variations to our program. We don't want any invariance to happen. So we want to make sure that if there is an error at some point during this flow of sort of like triggering the actual handler, we want to be able to capture that and send it back as part of the response so that the other side knows that there's been an error. We're going to wrap it with a try catch. And here, for example, we just stringify the error. There's a lot of different things you can do. Depends on how you want to handle it. But here we're just going to JSON stringify. We're going to send that back over. In our actual block, we're going to try to get the handler for the function. So we're going to check the API handlers. We're going to pass the function name in. If there is no handler, we're going to throw an error so that we know that there's no API handler. Now, this shouldn't ever happen in production, because the entire point of this is sort of, you'll then find out during development if you're missing a handler for something, if something is getting called when it's not supposed to, right? So we go ahead, throw an error, because we can't handle it anyway. And then next up, we call the handler, we store the response or the result, and then we send it back. We send the response back. Now there's one last thing we need to do, which is the cleanup. Now, we want to remove our message handler like before. Remember, we need to wash our hands. And then we're going to go ahead, if there is any, because we're cleaning up anyway, we're not expecting any messages to come in. So we can go ahead and basically reject any still active requests that are waiting for a response. And then we can go ahead and clear the entire map so that we clear out all of those references. We would also, again, I don't have it here, but you would also want to remove all of your, or like unregister all of your IPC handlers. But that's pretty much it. And so now I know what you're thinking, because I'm thinking it too. Just please stop. Please stop talking about all this stuff. But I promise we are done. So now let's take a look at what we're left with. So all of that. This is what it looked like before, right? So we had the creation of the process. We had this one kind of like big handler that would listen for everything. And this is what would have to be replicated throughout your application if you want to listen to messages from this. Then we also have to sort of like explicitly say what type it is. Yuck. Here's the sort of child process where, again, we have this massive listener that everything's inside of. We're like saying it's only going to be one type. We're having to force all of these types. It's just gross, man. And now what we have is something like this, where we have our creation of the child process. We're then wrapping that into 2 easy to consume APIs. And then we now have access to creating these listeners whenever we want, that can be cleaned up however we want, whenever we want, that don't have any boilerplate, are completely type safe for events. And for functions, for calls, we can directly access them. We can directly call them and just await the result and then use the result. And on the other side of things, it's the exact same. We have create worker API, we have event emitter, and we're able to just register a handler for specific functions, which are pretty normal. You have a function name, you have a signature, you do what you need to do, you just return the result. That's it. There's no boilerplate. You don't have to worry about, passing these IDs around and stuff. You can just use them. And then when it comes to emitting events, you can do that too. And it's all fully type safe. Now, I know it seems like we did a lot of things, and we did. It was definitely an investment. As you can see here, though, when you have this level of sort of, developer experience, you make this investment once and get the sort of like infrastructure, so to speak, in, you're left with something that's so much more maintainable and so much more kind of like simplistic to iterate on, that adding new features, adding new events, maintaining things becomes so much easier and such a nice experience. Because you don't have to worry about all of those edge cases. You don't have to worry about all of these different edge cases and passing the information here. You can just write the code that you need to write. And it is like an investment, so to speak. Like, you do have to invest time into actually implementing it in the first place. But you end up with a much more maintainable and usable code base that can do a lot more, right? So to wrap up, like, IPC is hard. It's annoying. TypeScript is hard and annoying. But again, if you put focus on establishing these sort of strict building blocks, and you spend some time on the kind of tooling around it, so to speak, iterating and maintaining your code base as it grows becomes so much easier. Now, that was long. I really apologize. But hope you enjoyed it. Hope you learned something. Again, all of this information, the entire presentation, is available on my website, ipc.banksfort.dev, as well as on my website directly has a link to this, and it has a link to my GitHub, to the repo on GitHub, and all of this stuff is available on GitHub, even the example app that was being shown there with all of the code in it. Feel free, grab whatever you need from it, and I hope that was beneficial. Hopefully you learned something. If you stuck around, thank you very much. I know it was long. I know it was tough at times, but really appreciate it. So thank you very much, and hope you have a great rest of your day.